Recording in progress. Okay, so good morning, everyone. Dr. Nat here. We are continuing with module number 10, but this is part 2, where we talked about estimator, point estimate, which is the actual value. The estimator is your equation. Are you seeing my slide? Can you see my slide? Yes, okay, great.
Yes, Doctor.
Okay, so we talked about point estimate. And I told you point estimate is actually the value, and the equation where you get the point estimate is called the estimator. And sometimes your point estimate can be different from your estimator, given that sometimes they already give you what is the value for your point estimate, which is theta. And remember, your estimator is your uppercase theta, which was, how do you write it? I think it was like this. Okay, so let's just assume this is uppercase theta. So sometimes they give you the equation and they don't give you the theta. Sometimes they give you the theta and both the point estimate and also the estimator. And from here, if we subtract the estimator with the point estimate, we would get the bias. Okay, it's in the notes last time. Estimator minus the point estimate. This is a given value. Okay, and this is the equation, and we're just finding the equation. We're finding the value using the equation, and this is the given value. And you find out that, our estimator is off by some value. So if it is off by some value, it will be greater or less than 0. This means that your estimator has a bias, whereas if your estimator minus your point estimate is equal to a 0, then your estimator is not biased, and that is great news. And then when we have several estimators, we talked about we should pick the estimator with the smallest variance, because that would mean that your data is less spread out, and this is what we want, our data to be more confined towards our population mean. Okay, so that was the point estimate and estimator, just roughly. And then we talked about confidence interval. Let me rub this off. We talked about confidence interval. Okay, so let me get back to confidence interval using this example. So the average zinc concentration recovered from a sample of zinc measurements in 36 different locations. So we know that our N is 36. Is found to be 2.6. So this is our average sample mean from our sample of 36 locations. So we know that this is a sample mean and it is not the population mean, right? So this is going to be 2.6. Find the 95% and 99% confidence intervals. So we have two questions here. We need to find 95% confidence interval, CI, and also 99% CI. For the mean zinc concentration in the river. So we are trying to find the interval or the confidence interval for our mean. Assume that the population standard deviation is 0.3. So this is our population standard deviation, which is 0.3. So these are our statistics. We have the standard deviation for our population. We have our sample number. We have our sample mean. Okay, so this is a recap for the confidence interval, even though it's a question. So the first thing to do, what is it? What do we do first? We want to find for A. What was the step? Does anyone remember? What was the confidence coefficient? Anyone? So no one remembers. Okay. 1 minus alpha is our confidence coefficient. And we equate this to what we're trying to find here, which is the 95%. So 95%, this is our confidence coefficient. If we multiply it with the percentage, we would get 95%. Now, if I'm getting rid of the 100%, I would get 1 minus alpha to be 0.95. Now, it is important for me to know what is alpha, which is 0.05 in this case, because I want to construct the interval of my mean. And we already know that from our previous class that this would be the sample mean plus with the value of CDF alpha over 2, and this would be standard deviation of the population divided by square root of the sample size. I think I got that right. Let me check the equation really quickly. So this was it. We want to construct our interval based on this. Okay, so going back. So this would mean that for my lower confidence bound, it would be C alpha over 2. Sorry, this would be a minus. And then we have our standard deviation over square root of n. So this is what we're trying to find. So the first thing is we need to find alpha, and then we need to know what is our alpha over 2, which is 0.025. So now I know that my z is z of 0.025. And we already know that 95% confidence interval is actually 1.96 from here. Remember that we talked about this last time? So if it is a 68% confidence interval, then it's just the standard deviation over the square root of n. And then if it is a 90% confidence interval, it's 1.645. And if it's 95, it is 1.96 times with the standard deviation over the square root of n. So you can find this yourself. Please refer to the previous video if you don't remember how to do that. I'm just going to take this value because we already discovered how to find the values for that. So that is going to be 1.96, right? So 1.96 times with the standard deviation of the population. So that is going to be 0.3, and our n is 36. So I'm just substituting the values over here. I'm recording, right? Yes. So this is 0.3. Same case over here. And this would be also 1.96 because it is a 95% confidence interval. Okay. So we know what is our alpha over 2. And then from here, we got our value for our z from the CDF table. And then this would be step number 1, equating this. Step number 2 is getting this value z. And step number 3 would be solving for our standard deviation over the square root of n. And then we get our confidence interval. So we already talked about these steps. So the answer for 95% confidence interval would be, this is what our x is 2.6, right? So I should write here 2.6, 2.6, 2.6. So my mean is between 2.6 plus 1.96 times 0.3 over 6. And this is the lower confidence bound. So I can write this nicely, but let's not do that because we already have the solution. So finally, we get that our sample mean is between 2.5 to 2.7. Here they are writing it as mu. But typically we say it is a sample mean. But remember, the sample mean is just equal to mu in the central limit theorem. Okay. So we are assuming a large sample size. This is a large sample size. It is 36. So they are equal. But it won't be the case if the sample size is small. Okay, so from there, I want to add on to what we know already. Any questions about the previous lecture? That was just a recap. Any questions that you're concerned, that you don't understand, you want me to repeat? So everyone's okay? Everyone remembers? Okay, I'm just gonna repeat myself here. So first, you equate the confidence coefficient to the confidence interval that you want. So this is number 1. Oh, let me use a different color. So this is number 1. Okay, and then number 2 would be to know what is the Z CDF from the CDF table. I want to know a Z of that gives me a 0.025 CDF, cumulative distribution function, or the probability from the table. So this is the value that I want. I want to know what is the Z. So if you were to refer to the cumulative distribution table, 0.025 would give me somewhere around here. 0.025 over here. So I would get minus 1.96. They are symmetrical. So I'm just looking at the lower boundary, lower bound, 1.96. So if I were to look over here, 1.96, where is it? It's here. So it is this value. So 1 minus 0.025 would give me 0.975. So this is the value that we got from our alpha. And then I want to know what is the Z. So the Z is 1.96. Okay, so this is where I got the 1.96. And then I try to find, so this is number 2, right? Finding the Z from the CDF table. And then number 3 is, equating it to the standard deviation over the square root of the n. So this is fairly easy. Then you multiply these two values and then plus minus with your sample mean. Okay, so I think this is okay. I already repeated myself twice here. So I'm going to continue with something new. So it is tempting to say that the probability is 95% that mu is between 2.5 and 2.7. So look at our solution here. We are saying that the sample mean is between, we are saying that our population mean is between 2.7 and 2.5, right? It is very tempting for me to say that, oh, there is a 95% probability that the population mean is between these two intervals. Because when we try to draw it, this is how we're drawing it, right? So this is our 2.5 and this is our 2.7, for example. So, and we are referring to the 95 confidence interval in this section. So it looks a lot like probability, but in reality, it is not probability because probability refers to random events, which can come out differently when experiments are repeated. Remember that we have variations between samples. The first sample can be 2.5, the second sample can be 2.55. They have the difference depending on the sample that you take. But for the numbers 2.5 and 2.7, which is the bound of the interval, they are fixed, not random. The population mean is also fixed. The mean population zinc concentration mean is either in the interval 2.5 or to 2.7, because this is what we specified. This is what we tried to find, right? And we are trying to find if the population mean is inside here. We're trying to find. Sometimes it is, sometimes it is not. There is no randomness involved. Since the population mean will not be exactly equal to the sample mean of 2.6, it is best to construct a confidence interval around 2.6. So we are constructing a confidence interval around the sample mean, and we're just trying to find if the population mean is inside this interval. But we don't know if it's really there or not. Therefore, we say that we have 95% confidence, not probability, that the population mean is in this interval. Okay, so I have my sample mean, I find the interval, I only have 95% confidence that my mu is inside this interval, 95% only. 5% of the other times, the mu is not inside this interval. So I'm only 95% confident, not 100%. Okay, I hope that makes sense. It's not probability. You're just being confident over an interval that your population mean is inside your interval. Okay. Okay, so you can read this on your own. It's just reiterating what I said earlier. Okay, so we already know that our sample standard deviation, our population standard deviation. Let me just go over this one first. Using the sample example given earlier, which was the average zinc concentration, the interval that we calculated specifies the mean to be within plus minus 1, right? So this is our sample mean. It was 2.6. And we found out that the interval was between this guy. This is our interval with 95% confidence. So assume that this interval is too wide to be useful. So this is plus minus 1, right? And you're saying this plus minus 1 is too big. I want something more specific. So assume that it is desirable to produce a 95% confidence interval, the same confidence that specifies the mean to be within plus minus 0.05. So instead of plus minus 1, you want your interval to be plus minus 0.05. So to do this, to change your interval to become smaller, to become more specific, despite having the same confidence interval, you need to increase your sample size. But to how much, right? So remember, our equation for the interval is plus z alpha over 2. Let me write this somewhere else. So sample mean plus with z alpha over 2. And then we have our standard deviation, square root of n. So from here, okay, forgive this thing. From here, I know that this is 1. This is plus 1, and I have another one over here, which is minus 1, right? Minus z alpha over 2 standard deviation over square root of n. And this guy is supposed to be minus 1. This is the plus minus 1 interval that we got earlier. Now, I don't want it to be plus minus 1. I want it to be 0.05. So if my population mean, I cannot change population mean, right? For sure, I can't change that. The only thing that I can change is just n. I want the same confidence interval, which means that I also cannot change this guy. Same confidence interval, population standard deviation cannot be changed. Therefore, the only way that I can make this smaller is to increase my n. Okay, so with that, I have a new equation. So let x1 up to xn be a large sample, random sample from a population with mean of mu and standard deviation of this guy, so that your sample mean is approximately normal. Then this follows the central limit theorem. Then a level of 100% times 1 minus alpha, which is your confidence interval, is the same thing that we discussed earlier, where same equation as well. When the value of your standard deviation is unknown, it can be replaced with the sample standard deviation of S. So this is basically our definition for the confidence interval. So if the confidence interval is specified, we can look up the value for our z alpha over 2. If the population standard deviation is also specified, then we can compute the value of n needed to produce a specified width. So let's go for an example. And we know that we have to use this equation to find our sample size. Okay, so how large a sample size is required? So I want to know what is my n. In the earlier example, if we want to be 95% confident, so this is going to be a 1.96 z alpha over 2, that our estimate is off by less than 0.05, meaning to say plus minus 0.05. The same question that I asked earlier. So instead of my interval being plus minus 1, I want my interval to be plus minus 0.05 from the sample mean. So this would be equal to z alpha over 2 standard deviation of the population divided by square root of n. So this is 0.05. So I know what my Z alpha over 2 is. It is 1.96. I know what this is, but I don't remember what it is. Let me check back. My standard deviation is this guy, 0.3. Assume that the population standard deviation is 0.3. This is the same example. So 0.3, so 0.3 over square root of n, 0.05. Now I can solve for n. Fairly straightforward, 0.05 divided by 1.96 divided by 0.3. No, I need to get this over here. So let me try that again. So I want my n to be the subject, right? So I'm bringing this guy over here. 1.96 times 0.3 divided by 0.05. So I have a square root n over here. Obviously, I don't want this in square root. So I'm getting rid of the square root by squaring both sides. So I'm left with n equals to 1.96 times 0.3 divided by 0.05, square the whole thing. So my answer would be 139. 139. So my sample size is 139. So earlier, when I got a confidence interval, when I got an interval of 1, my sample size earlier was just 36. So there's a huge difference in the sample size. This gives me a different interval. So you are more, of course, when you have a greater sample size, you can be more sure of your data, can be more specific, and you know, you get a better value, right? So it becomes closer to the mu with a confidence interval of 95%, of course. Okay, so any questions about this one?
So far, okay, Doctor.
No question, Doctor.
Okay, thank you. Okay, so we talked about two-sided confidence interval. Let's talk about this and then take our break, okay? So let's talk about a one-sided confidence interval. Previously, we were talking about two-sided confidence interval, meaning to say we have the upper bound and we also have the lower bound, and we know this is our 1 minus alpha confidence coefficient. If I multiply that with 100%, I get my confidence interval level. So this was one-sided confidence interval, and the Z was Z alpha over 2 minus here and plus Z alpha over 2 over here, and the standard equation. I'm just writing it down so that we can refer to it. Okay, so this is two-sided. Now, what happens if we only have one? Sometimes as an engineer, we don't really care about the maximum weight that something can take on. Sometimes we just want to know what is the minimum weight. Sometimes we want to know sometimes we just want to know the maximum, or we just want to know the minimum. Either or, right? We don't really care about both sides. We only care what's the maximum or what is the minimum for our creation or our innovation. So this is when we use the one-sided confidence interval. So let x1 up to xn be large. We are still following the central limit theorem here. A random sample from a population with mean of mu and standard deviation so that our sample mean is approximately normal. Then level of confidence interval, lower confidence bound for mu is sample mean minus z alpha times with the standard deviation of the sample mean, or this guy. Okay, it's the same thing. So here we have a different equation, not really different, but something different. So our Z is no longer Z alpha over 2. It's now Z alpha. Okay, so for one-sided, we only care about one side, right? Either the maximum, either the upper or the lower. Because of that, they adapt the two-sided confidence interval to become 1. So instead of alpha over 2 and alpha over 2 on both sides, they just take everything on one side. Therefore, you get your entire alpha, which is Z alpha. So now if we are predicting our lower confidence bound, then it would be sample mean minus Z alpha times with the sample mean standard deviation. And the confidence interval for upper confidence bound for mu is this guy, where this is the same equation that we talked about. When the value of your standard deviation of the population is unknown, you can use it. You can replace it with the sample standard deviation. Okay, same definition, except that now your Z alpha over 2 is now Z alpha. So it's just the same thing, except Z. So in particular, the values for your, what do I say? The Z alpha would be different, right? Because this is no longer Z alpha over 2, it's Z alpha. So previously we know that 95% confidence interval would give us 1.96. For 95% confidence interval, for upper confidence bound of a one-sided confidence interval, it is 1.645. So different values, of course, you can just find it as normal. So for 95%, you would find a Z of 0.05 instead of 0.025. So just use the CDF table and find out what is the Z. So let's do that. Do we really get 1.645? In case you don't remember these values, you can look up to the CDF table. So we want a value of Z alpha to be 0.05. Just now we were trying to find 0.025, right? Okay, so 0.05, I'm trying to find from the negative side because it's easier that way. So 0.05 would give me something over here. So here, I'm gonna take 0.0, 1.64. It is between these values. Let's just take one. It is between here. Okay, so I would get 1.645, around that, 1.65 or 1.64, 1.645. So if I'm talking about a one-sided confidence interval, I want to know what is the 95% confidence, 95% confidence interval, one-sided. So Z alpha is just 0.05. Then my value is 1.645 instead of the 1.96. Okay, so now you know how to find it. So there is no excuse to not remember these values or find it out yourself. Okay, so 1.645. So this is how we try to find the values. Okay, the rest is just the same. Okay, so let's go for an example, but let's take our break first. 7 minutes break, come back at 9:40. If you have any questions, you can ask me. Otherwise, take your break. I'll see you at 9:40 a.m. Okay, so it's time. It's already 9:40. So let's go for this example. Pretty straightforward if you have read it. If you have not read it, I'm going to read it. The article study on the life distribution of microdrills, the same example that we talked about earlier, reports then in a sample. You can see my slide, right?
Yes, Doctor.
Okay, great. So the article reports that in a sample of 50 microdrills drilling a low carbon alloy steel, same example, the average lifetime was 12.68 with a standard deviation of 6.83. This is from, I think this is example over here. Yes, study on life distribution of microdrills. So let's call this example star. So we talked about finding the confidence interval, 95% confidence interval for a sample mean of 12.68, and we had the standard deviation of 6.83, right? And we found out that this was our interval that we calculated. So the population mean is between here, oh my God, 12.68 plus minus 1.89. And we are 95% confident that the population mean is within this interval. So 12.68 minus 1.89. So this one should not have that minus sign. So this is what we discovered for our 95% confidence interval. So now we're going to use this same example and see how different it is. So of course it's going to be different because our Z alpha is different than the Z alpha over 2. So instead of using Z alpha over 2, we are using Z alpha, and for 95% that would be 1.645. And for the standard deviation of the sample mean, it would be over here, they already give the equation. The S is 6.83, our sample size is 50. So this would give me 0.9659. Let me just double check. 6.83 divided by square root of 50, 0.9659. Okay, that is correct. So you would just need to, if you are trying to find the lower confidence bound, find the lower confidence bound, 95%. So that would be X sample mean minus with 1.645 times with your sample mean standard deviation, which is 0.9659. So we are talking about lower confidence bound. So you have to minus from your sample mean. If we are talking about upper confidence bound, then you would just plus with your sample mean. So for 99%, let's go for this one. It is a 2.33 times with the standard deviation of the sample mean. So this is 2.33 times with 0.9659. So when we are trying to specify whether it's upper or lower confidence bound, for lower, it is a minus. For upper, it is a plus. But the sample standard deviation is always the same. For these two guys, they are the same. The only difference is your confidence interval, your confidence level, which is 95 or 99%, or depending on the question. Okay, simple. I think this is simple. You just apply what you have learned in confidence interval for two-sided. Now it's one side. Instead of Z alpha over 2, it's Z alpha, and the rest is just the same. Okay. So now we're trying to compare the values that we got. So for our, let's go for the 95% confidence interval. So the answer for our 95% lower confidence bound is 11.09. Okay, so keep that in mind. So it's 11.09. Now, this is the interval that we calculated for the two-sided. This is our two-sided interval. So the two-sided interval, this is your lower bound and this is your upper bound. This is your lower bound for one-sided. Now we can see that our lower bound for the one-sided interval is higher than our two-sided. It is higher. Okay, So let's try to explain why. So the 95% lower confidence bound is greater than the lower bound of the two-sided confidence interval. The reason for this is the two-sided interval can fail in both ways. Remember, when we're talking about two-sided, it can fail this way and it can fail this way. What does it mean by failing? It means that your population mean is not within your confidence interval. So you want your mean to be inside your interval, right? This is your prediction. But sometimes you fail, and that is the 2.5% over here and the 2.5% over here. The value goes here, and this is when you fail. So the two-sided interval fails in two ways, in the upper side and also the lower side. The value of mu may be too high or too low. The two-sided 95% confidence interval is designed to fail 2.5% of the time on the high side and 2.5% of the time on the low side. So this is different compared to the one-sided because you only fail in one side, because this is how you are designing that problem. So for two sides, we have these two sides, obviously. For one side, you're just talking about this guy. This is where you fail. Not you specifically, but the design. This is where it fails. So if we're talking about 95% confidence interval, this fail is 2.5% over here. If we're talking about one-sided, we know that this is just Z alpha, right? So this is exactly 5%. What about this side? No fail. It's just the way that the design is. Sometimes the design doesn't really care about the minimum weight. It only cares about the maximum weight. Sometimes it cares only about the minimum weight, not the maximum weight. So there's, how do I come up with an example that only fails in one side? Let's talk about a lift. Okay, so a lift or an elevator. If I'm designing a futuristic elevator, for example, I have a specific weight that there's no minimum weight for an elevator, right? I can just like put a feather inside the elevator and it still works. But if I put like 10 huge people inside my futuristic elevator, for example, sometimes it goes beyond the range that it works. So you want to know what is the weight that the elevator fails. Okay, the weight that the elevator fails. So if I want to specify a 95% confidence interval, so I would construct something that is going for the upper, right? Upper or the lower, but in this case, I'm going for the upper. When does it fail? So this would be the 95%, which is 1.645 standard deviation of the population over your sample size, square root. This is if I'm trying to find out like the upper bound of when the elevator fails. I can also find the lower bound of when the elevator fails, but I'm not interested. I just want to know the upper bound. So sometimes there is situations where I don't really care about the lower bound. I only want to know what is the value before the elevator breaks and everyone is trapped inside the elevator. So this is what we were trying to find. Only one-sided interval. The other side, the minimum weight, we don't really care, right? So there's only one way to fail, which is going beyond the maximum weight. So only one-sided interval that we want to know. So 5% is where our population mean is not within our confidence interval. Okay. So in contrast, the 95% lower confidence bound never fails on the high side. It is therefore designed to fail 5% of the time on the low side. So its lower limit is greater than that of the two-sided interval. Sorry, we were talking about lower limit, but I was talking about upper limit just now. So I hope I didn't confuse you. So let's go back to the lower limit. We're talking about lower limit here. So this is lower limit. lower limit. We're talking about lower limit. So 95% confidence bound never fails on the high side. So let me redraw this. Never fails on the high side, which means that it only fails here. It only fails over here. And this is where we are super confident for some level that our population mean is inside this, within this range, right? And this is where it fails at the low bound. So it is designed to fail 5% of the time on the low side. So its lower limit is greater than that of the two-sided interval. So it's greater because you have more space to fail. You have 5%, right? So it's obviously greater than the 2.5%. So you have that allowance. So obviously it's going to be greater, or you don't have to allow, you don't have to become too specific in the low bound because you have that 5% of, I wouldn't say tolerance. Let's just call it interval. You have that range, right, to go between. So the 5% is greater than the 2.5%. Therefore, your lower bound is greater. Okay, so this is an example. This is just applying. I'm not going to go over this. You can read this example. Fairly straightforward, I'm sure. If you have any questions about this one, you can ask me. As usual, I want to tell you about the confidence interval for the difference between two means. This is our last topic for this class, not for the module. For this class, before we end class, we have another 8 minutes. Let me just introduce you to this concept first, and then we're going to end class. So we're going to talk about confidence interval for the difference between two means. Just now we talked about confidence interval for two-sided, confidence interval for one-sided. The difference was the Z alpha over 2 versus the Z alpha. So now we're going to talk about confidence interval for difference between two means. So we have mean number 1 and mean number 2, or sample mean number 1, sample mean number 2. We're trying to find if our sample mean, if our population mean will be in between this interval. Let's just go for it first. Let X and Y be independent. We have two population where X is follows the normal distribution with this mean and this variance, and Y follows a normal distribution with this mean and also this variance. Then the X plus Y follows the normal distribution, whereby the mean is the addition of these two sample means. And for the variance, it is just the addition of these variance. If you're talking about the difference between the mean, then your mean is going to be mu X minus mu Y, but your variance is still, you still have to add them together. Okay, this is different. The mean is either plus or minus depending on whether you're trying to find the addition or the subtraction, but the variance is always a positive. I mean, it's always addition. Okay, so let's look at this distribution, normal distribution. The observed difference of sample mean X minus with sample mean Y is equal to 27, is drawn from a normal distribution with mean of mu X minus mu Y. Okay, and the standard deviation is this guy, your squared plus this guy squared. So if you're trying to find the standard deviation, you have to square the whole thing. So this is the summary for your confidence interval for between the difference of two means. So instead of sample mean plus minus Z alpha over 2 for your two-sided, you have this. Your sample mean minus sample mean X minus sample mean Y plus minus Z alpha over 2. And your, basically this guy. Okay. So I'm going to change this. Okay. Plus minus the alpha and your standard deviation for the difference in the sample mean. Just now we didn't have this. We didn't have this. So now we do. So it's different now. So it's just applying equation, fairly straightforward. let's go for this example in our next class. The end. So all the best for your exam. Do your best. And I'll see you tomorrow. No, not tomorrow, next week. Okay, bye guys. Have a great rest of the day.
Thank you very much, Doctor.
Thank you, doctor.
Bye.
Doctor.
Welcome.
Thank you, Doctor.
Bye.
Doctor.
Welcome. Bye guys. Baliklah.
Bye, doctor.
Bye. Good luck.